Hello everyone. Today we are going to talk about mathematical models and elementary functions because when we look at the real life problems, for instance, the size of a population, the demand of a product, or the cost of a product, or sales of some product, or the speed of a falling object, uh, concentration of a product in a chemical reaction, telecommunication systems, DNA molecules or those molecular structures of um, chemicals, all kinds of stuff we can think about. They can be actually modeled, and in these models, we will need mostly some elementary functions. Today, we are going to talk about these elementary functions. First of all, for instance, if we have some linear model, then we can express this model with a linear function. What do I mean by a linear model? Let's say you have some data given by some table, and then when you plot the points, let's say you will have points like this using the table. You will have points scattered in the xy plane. So this can be approximated by some linear function like the closest line passing through maybe some of the points, but this line can be used to express this linear model. So this is a linear function to express the linear model we have. Of course, there is a name for this modeling. If you have seen machine learning, this is called actually linear regression. So regression means you approximate your model to something mathematical, and then what you get is a linear function. So that kind of approximation is called linear regression. This is actually something um, used in the machine learning. This is actually a machine learning algorithm. So you have some table of some big data, you scatter it in an XY plane, and then if it could be expressed via some linear function like this, it's actually called a linear regression. And then this linear regression will give some linear function which can be used to predict other results for other x values. Okay, well, these linear functions actually have a common formula. Let's write this thing. So the formula is y equals m times x plus b. So here, y and x are the input and output axis. B is where the line intersects the y-axis, and m is the slope of the line. So basically a linear function, when you graph a linear function, you see a line graph, and it's actually, if you draw a right triangle here and call this thing delta x and call this thing delta y, m is nothing but the delta y over delta x, or rise over run. So if we run delta x times, then the graph will rise delta y times. So the ratio of rise and run is the slope of the line. So this is a very basic model. And another model is, well, most of the times, the quantities we have will have, well, more complicated graphs. Like for instance, you can have some table, and then if you plot the points, you may have something like this. And then when you make an approximation for this, it may be some function like this. Well, for instance, in my case, I wanted this to be some graph of x squared. Okay, so this is some algebraic function. Of course, it is more rigid. We can talk about it more rigidly. However, this x squared function can be used to approximate some other models. So if we have a model which can be expressed like this, they have a name as empirical model. So if, let me write the definition of empirical model. So this is used if there is no physical law to help us formulate a model, then we construct an empirical model, and most of the empirical models, empirical model, let me finish, which fits the data we have or at hand. Okay, so in these empirical models, most of the functions in the we will have to use are actually some kind of functions I'm going to talk about. In most empirical models, we will have algebraic or power functions. These are x, x squared, x cubed, or square root of x, which is also x to the 1 over 2, or let's say cubic root of x, which is x to the 1 over 3, or any kind of power function like x to the n. Okay, so these are one type of elementary functions. The other functions are exponential or logarithm function. By the way, we will talk about the logarithmic function later also, which is actually the inverse of exponential. So these are like e to the x, 2 to the x, 3 to the x. By the way, e is a number, 2.718 ... It's a number like pi, which is 3.14159, which is, the ratio of the circumference of a circle to the diameter. It's a transcendental number. Just like that, e is a number like that. We will see why we call it e when we come to the derivative business, because it's a very special number, but we will talk about it there. The log functions could be log 5 of x, for instance, or log 100 of x, so on and so forth. Again, these functions will be seen mostly, growth. This could be investment or population growth. We see these kinds of functions. Or they could be also seen in decay, like decay could be radioactive decay or temperature decay in some environment, We see these kind of functions, and these are very natural functions, by the way. And then the third type of functions are trigonometric functions. So the trigonometric functions, these are the footsteps, traces of rotational movements. So we could see, like some kind of trigonometric function if there is some kind of rotational stuff going on. These functions, again, I will talk about them more. Sine, cosine, sine of x, cosine of x, tangent of x, cotangent of x, and there are two more, secant of x and cosecant of x. So these functions, when we try to analyze mathematical models, when we have some data given, these are going to be the functions which will come to us, and we will have to deal with these functions. So if we know what these functions do, how they look like, how they work, then it will be quite easy for us to deal with more complicated situations. Okay, now let me start with first let me start with polynomials first. Polynomials are nothing but some kind of power functions, but maybe I should start with power functions. Okay. So power functions are in the form x to the n. So x is a variable and constant power. So for instance, if we have, let's say, f of x equals x squared, as you see, n is 2 here, and if I have f of 1, then 1 squared will be 1. If I have f of 5, then 5 squared will be 25. So this is how it works. Or we could have some function like this, x, let's say, cube. Here n is 3, and if we have, let's say, f of 2, then we have 2 cubed, which is 2 times 2 times 2, 3 times. So the 3 here is the number of times 2. The input is multiplied by itself, which gives 8. So we can go and make this example for other power functions like, x to the 1 over 2. What is this? This is actually a radical function. Here the denominator 2 is the root and 1 is the power of x. But we shortly write this square root of x. The square root of x function, for instance, if we take f of 4, then square root of 4 is 2. This is another power function example. Let me draw their graphs very briefly. Like x squared function looks like this. This is x squared, x, y. X cubed function looks like this. Okay, and square root function looks like this. It's only defined for positive numbers. This is the positive part, this is the negative part. As you see, there is nothing defined for the negative numbers. And it starts from 0. This is 0, by the way, the intersection here. And it goes like this. Another example, let me give. is, let's say, cubic root. So that means I have the denominator is 3. So that means I take the cubic root of x to the 1, or simply we write cubic root of x. The graph of this function looks like this. So it looks like kind of square root of x, but it is also defined for negative numbers like this. Okay, why is this so? Because in the first case, like square root of -1 is not defined. We don't know what the square root of a negative number is. So therefore, the square root of x is not defined for negative numbers. So there is nothing going on for the negative part. Okay, so let me draw the graph like this, maybe. But in this case, we can talk about cubic root of -1 because we can write -1 as -1 times -1 times -1, because think about it, if you multiply -1 3 times by itself, it is still -1. So we have -1 cubed, and then we can write this expression as 3 over 3, which is -1 to the 3 over 3 is 1, and any first power of any number is that number again. So we have also numbers defined, we have also values defined for negative numbers. So the cubic root of x function will be also defined for negative numbers. Okay, so another example is this one. Let's say we have x to the -1. In this case, n is -1. Now, what does this mean? If you have a negative power, that means you can write this with positive power if you write that x to the whatever power to the denominator. But x to the first power is equal to x again. So f equals x to, f of x equals x to the -1 is nothing but 1 over x. So when you sketch the graph of this function, you are going to see a graph like this. Okay, let me just go slow, I guess. So if I have the xy plane, then the graph of 1 over x will look like this. Okay, and it's undefined only for x equals 0. Why is this so? Because think about f of 0. It's going to be 1 over 0, but dividing any number by 0 is undefined. But if you think about it, if you divide 1 by a very small number, something like here, let's say this is 1, let's say this is -1. If you divide 1 by something very small like this one, let's say 0.1, then you are going to get some number like 10. But if you divide 1 by something bigger than 1, let's say 10, then you are going to get 0.1. So the bigger the x value gets, the smaller f function will give. Okay, similar in the negative number case. So these are called power functions. Okay,